Going.
Yeah.
So let me first welcome everyone to MIT Inotherm. This is the MIT International Colloquium on Thermal Innovations. Um, really happy to have everyone here. And really happy to have the panelists and the talk we're going to hear today from Professor Bob Laughlin um, on the Brayton battery. So very exciting to get everyone together for this. We've been doing this every week for the last few weeks. This is the third installation. We have upcoming sessions on HVAC systems and getting the heat out. After Ken Goodson's talk on June 3rd, this will convert to a bi-weekly seminar series. So instead of being every week, it'll be every other week. And today, I just wanted to announce our host for today's session is Dr. Craig Turchi from National Renewable Energy Lab. He's a group manager there in the Thermal Energy Science and Technologies group. Um, he's a chemical engineer by training and has worked at a number of different places previously. And I specifically know him through his work on concentrated solar power. So with that, let me pass the mic to Craig so he can officiate this session.
Thank you, Ashi. And I appreciate the opportunity to moderate today's session. So as we've done in the colloquium previously, we're going to start with a couple of poll questions just to kind of set the stage for the discussion today. And these have been offered to us by Dr. Laughlin. So our first question you'll see concerns what fraction would the world's grid capacity have to expand if the world's transport switched from gasoline and diesel to lithium-ion batteries? And I'll ask the attendees to go ahead and vote, and you'll see the polling change as folks vote. So we'll give you a few seconds to ponder that question.
It's so cool to see the results live.
Isn't it? Isn't it?
Little race.
It's also interesting.
Mm-hmm.
So I think we're kind of honing in on a consensus vote of about 40%, which I believe Dr. Laughlin will confirm is the correct answer based on his investigation and published data. Do you want to comment on that, Bob?
Sure. That number is from official energy numbers from governments around the world, and my source, which is the BP Statistical Review. It assumes that the thermal efficiency of electric cars is 100%, which it isn't exactly, but it's awfully high. And also, it assumes a conversion, an average thermal efficiency of the oil and gas, let's say oil sector of 20%. So there's slop on that number. So it could be as high as 100%, but certainly not 150.
Yes.
Cool.
So clearly, as we electrify the transportation grid, there's going to be more need for infrastructure in the electricity grid. And if we want to power that grid, we're going to need to have energy storage options available to us to do that in an efficient manner.
Well, or more gas turbines,
Ah. Okay, I've got one other poll then. Let's see, poll number 2. So this poll concerns geothermal energy. What fraction of the total energy budget of civilization does the total geothermal, geophysical heat flow out of the earth constitute? So essentially, can geothermal energy be counted on to meet all of our future energy demands? And note that this does include the subsurface of the ocean. One's a little
This
trickier.
this is interesting too. It's just interesting.
Huh? You figure in the ocean occupies, of course, 3/4 of the world's surface, and yes. Okay, it looks like the consensus opinion here is a relatively low answer, about 10%. The actual answer here is 200% if you factor in all the thermal releases, including the subsurface. But there's a caveat on that, Dr. Laughlin has noted, in that much of that energy is at a temperature that's really too low to be useful for for powering the human environment. So depending on how you want to figure those numbers, it's upper bound about 200%, and the lower bound in terms of high temperature energy, more like 50%.
Yeah, and that assumes that you mine all of the black smokers under the sea, which is where most of the heat comes out, and that's kind of an expensive proposition.
Right.
The total heat flow number actually, you might imagine mining that with a whole bunch of thermal wells, but the expense of that is insane. So I think the real answer is that geothermal can't do it.
Right. A contributor, but not a solution to the whole problem.
Yeah, well.
So 10% is probably a more realistic expectation. All right. Thank you all for participating. So with that, we're going to move into Dr. Laughlin's presentation, and I'll have the honor of giving a brief introduction for him. Professor Laughlin is on the physics faculty at Stanford University in California. He did his undergraduate work at UCalifornia, Berkeley, and received his PhD at MIT. He subsequently worked at Bell Laboratories and Lawrence Livermore National Laboratory before coming to Stanford in 1984. His chief background is in semiconductors, but he has worked broadly in other areas, including nuclear energy, quantum magnetism, superconductivity, biological length measuration, and thermomechanical storage. In 2013, he co-founded a company known as Gigawatt Day Storage Systems, which later supplied key intellectual properties to Malta, Inc., which is a spin-off from the Google X skunkworks. He's the first author on 11 patents pertaining to thermomechanical storage and co-author of one more on quantum magnetic theory memory. He's the winner of numerous prizes and awards, including the Department of Energy's E.O. Lawrence Award for Physics, the American Physical Society's Oliver E. Buckley Prize, the Benjamin Franklin Medal for Physics, and of course the 1998 Nobel Prize in Physics. During 2004 and 2006, he served as president of the Korean Advanced Institute for Science and Technology. He's the author of approximately 150 works, including 4 lay accessible books, and 1 being on energy. He's a member of the American Physical Society, the American Academy of Arts and Sciences, and the U.S. National Academy of Sciences. Clearly an impressive resume. Let me turn it over to you, Bob.
Okay. So we're sharing here. Share. Okay, have we got signal? My own voice is not coming to me. So, Craig, you can communicate with me with hand signal. I can hear you, yes. Okay.
Yeah, we can hear you fine, Bob.
I can't hear myself. Okay, great. Well, gosh, hello, everybody. I don't want to say good morning or good evening because I'm not sure where you are, but it's nice to have you here and nice to be with you. I'm going to talk today about what's on the screen here. And there are 2 relevant publications you see at the bottom. One is in press. The other one's been out for a couple of years. Before I get deeply into this, I want to note that the publication date on the first one is 2017. That paper was actually written in 2013, but it was embargoed. And that whole question of privacy and secrecy and embargoing and so forth is actually very relevant to the bigger question we're talking about this morning. So I'm going to talk to you about technological things having to do with how to store energy on the grid cheaply in enough mass to have an effect on the economics of wind. This little item is an example of what it might look like. This is drawn courtesy of Brayton Energy LLC up in New Hampshire. I don't want to talk a great deal about it other than to say first that this picture came out in 2017, which is not an accident. And also you'll see that yellow thing says heat pump. That's the engine. And this particular version of the engine is bigger than it ought to be. So the actual engine that's doing the conversion of the energy is actually very small and is separate from whatever is storing the energy. And that separation between the engine and the storage medium is actually critical for the economics. Now, let's begin by talking about what I call the problem. Like everybody to look at the bottom figure. That is the world energy budget in joules per year as a function of time from the BP statistical review. This is converted from tons of oil equivalent by the usual factor. Here, the key things to note are first, that the total growth is monotonically upwards. Secondly, the total renewable budget is that little yellow sliver there. That's all of wind and sun. Now, plus, it turns out it also includes corn ethanol. And that's important because the energy economics of corn ethanol is very problematic because of the diesel used in growing the corn. So actually, the renewable situation is even worse than that yellow sliver shows. That renewables are growing very rapidly, about 2/3 of that yellow, but the fossil consumption is growing faster. And the total growth in the coal, natural gas, and oil actually exceeds the advances in renewable energy. Now, at the top is the Keeling curve. So this is the measurement of carbon dioxide concentration as a function of time at the top of Mauna Loa in Hawaii, and you see it's monotonically going up. Interestingly, if you go to the bottom figure and add up all the carbon and assume that it's distributed uniformly in the atmosphere, you get about twice this increase. So that means the Keeling curve is missing about half the carbon budget out of the Earth, and presumably that's going into the oceans, although you don't have direct proof of that. All right, so that's the energy carbon situation. Now, we get to electricity, wind, and this is what I call the problem part 2. This is a plot of the power budget of the state of California. The California ISO is a function of time over 24 hours in some day in 2009. What you see here are 3 curves. The gray curve down there is a prediction made 3 days ahead of what the demand will be. The red curve is a snapshot of what the demand is in real time. You see it matches the curve pretty well. And then the green curve at the top is reserves. So the reality of electricity today is that electricity travels at the speed of light and is not storable. So power companies make their business by anticipating what demand will be and then switching on generation assets onto the grid in time to meet that demand. And that's so sensitive that they have to have extra on hand just in case their theory's wrong. Notice the magnitude of the slosh there is about 30%. Call it 50. Okay, so it's because of where 0 is on the y-axis. So it's what I call the diurnal surge is about 50% for the electric grid between low use in the early morning and high use at rush hour. As a result, wind assets often have negative value. This has happened in numerous parts of the world, West Texas, parts of Europe, definitely in China. The wind energy comes when you want, and the fundamental problem here is that the power industry is all based on time. Power that comes when you don't need it is useless to the industry because the industry is busy switching on assets to balance the load. So negative value means that the power is worthless. It's worse than worthless. You have to pay the grid to take your power. So this is telling you that there's a business problem that's fundamental and has at its root the physical reality that electricity can't be stored. Now you say, well, why not store it? Okay, there's a really interesting fact about the United States, which is that it has a huge amount of pumped hydro storage available, particularly in the Appalachians. And these are 2008 numbers. The amount of pumped hydro storage that you have down at the bottom, that red 0.25, is 1/4 of the amount you would need to level the entire diurnal load of the surge load of the country. So this was built chiefly in the 70s and 80s, and you might ask, well, just why not build more? Clearly, if you build 1/4 of it, you could build the rest. Well, that's part of the story. One reason, it's the lesser important reason, is that there's a danger factor. This is a picture of the famous Tom South breach where, well, I think the picture is self-explanatory. The reservoir failed and there was massive destruction downstream of it. But the more important lesson is that the amount of energy we are talking about storing up the surge for a metropolitan area is an immense amount of energy. It's equivalent to a really hefty sized nuclear bomb. So that means when you're thinking about energy storage as a safety issue, it must be physically impossible for all that energy to come out at once, or you risk destroying the city. So for example, storing all that energy in compressed air above the ground is kind of a non-starter. All it would take is one terrorist bazooka round lobbed into the middle of the tank farm and no more city. The much more relevant reason is this. In the late 1980s, aeroderivative gas turbines got to be very, very good. And the power industry discovered that it could handle that surge much more readily by buying cheap gas turbine generators, simple cycle gas turbine generators, and just switching them in and out of the grid as the needs of the load required. And this is the way it's done today. So when this technology came on board, construction of pumped hydro stopped. In other words, what stopped the construction of the remaining 3/4 of the pumped hydro that you would need to level the load is economics. Basically, the gas turbines were cheaper, and there was no hassle with the government over land and no water to deal with, and they're faster. So there's a technical / cost issue right at the breaking point of where power companies make their profits. Now, let's talk very specifically about those profits. This, look at the bottom, this is a plot, again, for the California ISO of the total power, basically of all of California versus time over 24 hours, broken up into components. This is for a particular day. It turns out it's the 1st of April, 2019, but it doesn't matter. It typically looks this way every day. And what you'll notice is that big yellow bulge down at the bottom which is basically the solar fields from the Mojave. And you'll see that it's a big hunk of power. It's about 10 gigawatts. Just to put that in perspective, the average power needed by 5-county LA Metro is about 14 gigawatts. So it's a lot of power, and you'll see it rises up while the sun is shining and then dies down during the day. And then the total power use at the top, you'll see peaks way later. It's peaking about 2000. On this particular day, the various power utilities balance the load with the red, which is gas turbines, plus hydro imports from the Pacific Northwest. So out in California, we're near enough to Washington that we can use power lines to bring down power from Bonneville, and that's dispatchable. And the gas turbines are dispatchable. So while that's the case, you can balance the load with those things. Now, that in mind, look at the top. This is a plot of California's battery flow. And you will see that it's in the same units, which is in gigawatts. And you'll see it's going up to 0.1 gigawatts, we say 100 megawatt. And it's going up and down in sort of 20-minute intervals. Now, what this is telling you, okay, well, what that is that's battery facilities regulating the grid phase. And so they do that very well, and but they do it to the tune of 1/10 of a megawatt. In other words, this red line here, if plotted on the bottom, wouldn't even show. Okay, it would just be this noise. So what this tells you is that there is a business model for using lithium-ion batteries to balance the grid phase, but there is not a business model for using it to balance out that big yellow bulge. So short time scales, batteries will do very well. 20 minutes is okay, but when you get out to 6 hours and so forth, the cost numbers aren't working. And you know this because if they did work, those battery people would be right in there balancing out that yellow bulge. Okay, so there's a money problem that has to do with time, and the time scale is some number of hours. Now, in order to identify this time scale, we have to go into the twilight zone. And what I mean by this is to deal with prices. And the problem with there, of course, is that pricing has to do with human behavior, and you don't actually know what costs and prices are until you're in business selling things. So these numbers have very large error bars, and we could argue about them, but I have to put something, so I'm going to put these numbers. So here we have cost in dollars per watt for the storage as a function of how many hours of storage you got. Okay? You notice right away, my thing, which I'm talking about today, is red, and it's the best. Why is that so? Because this is my graph, and I get to make whatever I want best. Now, I'll try to justify it, of course, but there's obviously a conflict of interest with regard to the red line. What I want you to look at first is the blue line. The energy storage has two metrics. One metric is the total cost of the engine. That is to say, in the case of pumped hydro, it's the cost of the dam and the generators and the turbines. That's a fixed cost, and it doesn't depend on how much energy you store. The amount of energy you store depends on the size of the lake. And the lake can kind of expand, and there's land cost for that, but it's actually very small. So for pumped hydro, the line is flat. There's the cost per watt of the dam and the generators is what it is, but then the cost of the storage itself is very low. The slope of this line has units of dollars per joule. Dollars per stored joule. So the two metrics are the intercept of this line on the left-hand edge of the graph, which is the cost of the engine on the one hand, and then on the other metric is the slope, which is the cost of marginal cost per stored joule. Now, next, please look at the green lithium-ion battery lines, and you'll see they're sloping upwards. Now, that slope upwards is sort of central to the conversation. The reason conventional batteries do that is because they can't separate the storage medium from the engine. The engine is the electrode, and so when you buy more battery, you have to also buy more engine. And that means the cost per stored joule, which is the slope of this line, is quite large. Now, so if we go to the very left graph where there isn't much storage, you'll see that batteries are winning because they're basically very cheap. So that's it. No, for short times, batteries are going to win. This is lithium-ion cost today, but the cost of batteries can only be less than that. So these other technologies are not competitive for short storage times. But when we get out to about 4 hours, there's a crossover. And it's because of this problem that conventional batteries have a big slope because you're buying engine when you buy storage capacity. Those two green lines, by the way, are cost today versus projections. And I put the projections in dashed line because they're science fiction. We believe Elon Musk. These lines are going to, costs are going to go down. I don't myself believe Elon Musk. I think the costs are very close to where they're going to be today. But anyway, either way, the crossover with pumped hydro is about 4 hours. And this is a number that we know. So this is kind of the reason that the 6-hour solar bulge in California can't be balanced by batteries. Now there's a flow battery curve up there. Flow batteries and pumped thermal storage are similar conceptually. For now, I'd like to not go down the flow battery avenue. Let's just say for now, they have cost problems having to do with the electrodes and the electrolyte and the acids and the particular ions you're using in them and so forth. So flow batteries are a great idea, but they're kind of not ready for prime time cost-wise. Now, going back to the lay of the land here, I want to switch gears and talk a little bit about Spain. This is, here we are in southern Spain, Andalusia. This, by the way, is a promotional picture that I got from Die Zeit, the German newspaper Die Zeit. You'll see a Moorish castle in the foreground, and in the background, you'll see a big solar collector farm, which turns out to be Andasol 1. The length scale of that square thing is about 2 kilometers, kilometer and a half. Here's a close-up of it. And what I want you to do now is focus in on the center there, and in particular those two brown tanks. The center is where the engine is for this solar farm. So, and there it is. You see in the background we have parabolic reflector collectors, and in the foreground there are two tanks, and these tanks are filled with molten nitrate eutectic where heat is stored. So Andasol 1 was the first commercial plant that stored heat, energy in the form of heat collected from parabolic fields in molten salt. Now, this was not the first deployment of molten salt storage. That first deployment was at Solar 2 in Barstow, California, but this was the first commercial one. And because it was commercial, there was a lot of buzz in the finance markets about what the costs were. And because of this buzz, you can go back and look and verify that what the costs were, and see that they're actually remarkably reasonable. The fact that the plant was built also proves this, but let's just say that there's more evidence than that just because this was the first. Now, very quickly, this is 2008, very quickly the design proliferated. This is an NREL table, and it's not up to date, unfortunately. There are more entries. But the message is this. The fact that this happened tells you that the investors thought they could get their money back. In other words, the investors looked at Andesol 1 and calculated that they could make money at Spanish tariff rates building these plants. And so quickly, the design proliferated around the world. You'll notice that it's 50 megawatt. Why is that? It's because the Spanish government wrote laws that they would only subsidize the tariffs for 50 megawatts or less. So the initial designs were 50. In other deployments, particularly Morocco and the Middle East, they're more like 100, which is kind of what market wants. So what we know from the lay of the land here is that, first of all, that the molten salt storage of heat works, and secondly, the investors think it works. And mostly what these investors are paying for is the solar fields. So this is a really good sign that you've got economics under control. So back in 2011, I was thinking about this problem and getting more and more depressed because clearly heat storage works very well with the sun, but it won't work with the wind, and most of the alternate energy in the world is wind. And unfortunately, this wouldn't work for the wind. Then I realized, it will. And so that's what I want to tell you about now. So why is this true? It's because energy storage is actually not about energy. It's about entropy. So if you manage to have an apparatus that doesn't make any entropy, it will store energy reversibly no matter what. So the key to thinking about storage is to look at the entropy budget and see where entropy is being made. And if you don't have a lot of entropy being made, you're okay. You can do all sorts of nutty things that don't seem obviously doable, but in fact are. Now, the key observation here is that modern gas turbine technology has become very good. And the gas turbines are basically just a bunch of fans. Disregarding the burning of fuel a moment, the actual compression and expansion that occurs in modern gas turbines is very, very efficient. They make shockingly little entropy. And therefore, you can imagine running them backwards. Now, this is running them backwards figuratively. There are blade shape issues that you have to worry about, which I'll come back to later. But you can, insofar as there isn't any entropy being made, you can simply run the movie backwards. So you're producing energy, you stop the projector, run it backwards, and you're storing. Now, let me remind everybody about a few basics of gas turbines. So here you've got a jet engine and some air is coming in and there's some fire and air is going out and you get power out. And then you ask the question, well, how come energy is coming out? What's the difference between the compressor and the turbine? Turns out very few physicists know this answer to this, so I'll tell you. It's the temperature difference. So the key trick is that the temperature, it's much hotter at one end of the chamber than the other. And the work done in the turbo machinery is PDV. It's the DV. It's the volume is different in the two sides. So the trick is you keep the temperature unbalanced and then maintain that temperature imbalance with a stupendous flow of moles of gas through the turbine. Now let's advance a little bit and get rid of the fame and put instead the moral equivalent of a locomotive boiler in there. Then do exchange with some sort of heat fluid. Well, as far as the turbines are concerned, nothing has changed. They work exactly the same way. But now you have heat being transferred inside a heat exchanger such that the temperature difference over which it's transferred is very small. And if you do that properly, you can cause the amount of entropy made to be very small. So now here's the engine. Let's just do it twice. Copy it, have a high pressure side, a low pressure side. So we're doing the same thing gas turbine does, but now it's all done. It's external combustion, but it's not combustion at all. It's just stashing of heat in heat media. The one that's actually viable is something called a recuperated version, and let's not worry about that now. It's just something that you do with gas turbines that's common and works. Okay, now, so here we are in an ideal world where everything is adiabatic and the turbines are perfectly reversible. And we have two heat flows in the charge cycle, which I've shown here. The yellow thing is the recuperated region. There's the purple arrow is bigger than the blue arrow, so that's how you store energy. Now, it turns out that the storage medium deployed in the Spanish solar plants is fabulous. And I'd like to call your attention to that vertical green line there. That's the temperature range over which it works. And it turns out that that temperature range is large enough that phase transitions don't matter. In other words, the equipartition is guaranteeing that the amount of heat stored per atom is very large. And in fact, you don't want phase transitions to occur here because they're entropy makers. So this is an application where phase transitions in the medium would actually be bad. This temperature range turns out to coincide exactly with what's called the creep cliff of the steels in question. And this means that there's a fundamental compatibility with the engines. This compatibility is also manifested in modern day supercritical steam plants, which is why they have the temperature ranges they do. So the temperature scales of these salts turn out to be just perfectly adjusted for cheapness and compatibilities with materials. The actual cycle isn't adiabatic, of course, it's non-adiabatic, so the compression ratio has to be slightly different in charge and discharge, and you have to get rid of some of the heat. And here's a little formula calculating how much entropy the turbine and compressor make. That entropy has to be dumped into the heat, into the environment, and there's a little equation at the bottom, which is standard physics. Ta-da, 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 0.7. Okay, so with the extant gas turbine blade technology that one has today, we're talking about an asymptotic round trip efficiency about 0.7. That is enough to make money. Now, closed cycle gas turbines are not new. The first one ever was actually built in the eve of World War II in Zurich. The only truly new thing is the idea of running it backwards as energy storage. So lots and lots is known about this, and this particular engine is the progenitor of what we now call supercritical CO2 technology. Now, given that the darn thing is a money problem, what you as a technologist have to do is learn a whole lot about money and legalities. Politics too, but money and legalities. So the aftermath of all this thought that I just described to you is a whole bunch of patents. These are the ones that have been granted, and there are others. The reason you have to do this is because when you have a money problem, the people with the money have to put their money down on the table to get things to happen. And they can't do that unless they're protected. So you ask, what do you have to do to solve this problem? Well, what you have to do is get a whole mess of patents, so the money people can put their money down. So this particular technology I am banking on because it does what you need with the efficiency you need, with the economics you need. So we don't have a siting problem. You don't have to put the compressed air underground in caverns. Why? Well, because this technology is compressed air energy storage, except you do a secondary expansion first, so you don't have to put the compressed air in underground. And anyway, we all know when you compress a gas, the energy is actually stored in its heat. So there are heat issues with case that you just get rid of when you don't have the underground cavern. Because everything is at 1 bar, explosion is physically impossible. So the atomic bomb danger of energy is gone. All the problem of using public lands goes away because you don't have to make lakes. The footprint of the technology is quite small. Environmentally, you're in good shape. You don't have any pH2 stuff in giant tanks. You have just a bunch of salt, and if there's a breach, what happens is fertilizer goes all over the ground. And finally, no semiconductors. So as I said, I'm a semiconductor man, and I understand the physics of what's going on with the grid well enough that I know that you don't want semiconductors. Semiconductors, the grid is set up for mechanical motion. The grid is mechanical motion, like these horses, except it's electrical mechanical motion. And so faking it with semiconductors is actually bad and results in losses. So we get rid of the semiconductors and we're back to good old mechanical grid. We're done, and I'm on time, everybody. Thank you for your patience. I hope you were entertained.
Thank you, Bob. So I'd like to encourage everyone to submit questions if you've got them based on Bob's presentation or other questions you may have related to energy storage. And with that, we'll quickly move into the next part of our presentation, where we have a number of other speakers who will give a brief summary of some of the activities that they're working on to address this problem. So our first speaker will be Alejandro Datas. He's an assistant professor in the Institute of Solar Energy at the Polytechnic University of Madrid. He'll be followed by Dr. Ashigan Henry, associate professor in mechanical engineering at MIT. Dr. Mahesh Venkataraman is a materials researcher at 1414 Degrees Limited in Australia, which is named for the melting point of silicon, so you can get some idea of the energy storage approach that they're looking at. And finally, Mr. Andrew Ponick, who's the CEO and co-founder of Antora Energy in California, who is developing a low-cost thermal battery technology for grid-scale storage. So we'll start with Alejandro. I've got a couple slides, I think, Alejandro, and a summary of what you're working on.
Yeah. So you're going to share slides, or I should?
Do you want me to show the slides?
No, okay. I will go for it.
Yeah, share your screen to be easier.
Okay. Okay. Good. I hope everyone can see this screen.
Yes.
Okay, perfect. Okay. So thank you very much for the introduction. I will briefly, in just 5 minutes, introduce this concept of what I just call latent heat thermophotovoltaic battery. Well, as it is already said in the name, it has mainly 2 parts: latent heat storage and thermophotovoltaic conversion. Well, for the storage part, I want to emphasize the role of phase change material. Basically stores energy when they change from solid to liquid phase. And here I show the latent heat of these materials as a function of the melting temperature. So you can imagine that we want to have a high latent heat because this means high energy density capacity. What you can see here in this graph is that generally when you increase the temperature, the melting temperature, you increase also the latent heat, so the energy density capacity. And with some exceptional cases, like you can see here, the case of silicon or boron, or even this new phase change material that is an alloy of iron, silicon, and boron, they provide remarkably high latent heats. That is basically twice that of the energy density of electrochemical batteries, for instance, that are, this bar is illustrating them. Besides of that, you have a very low cost because this is just metals that are in the case of silicon, for instance, you have a euro per kilogram, which translates in €4 per kilowatt hour. So it's really a way of storing energy. Well, the thing is that you have a melting point that's really high. And what happens at high temperatures is that radiation becomes a dominant heat transfer mechanism. So this means that you can directly convert the light radiated by these hot bodies into electricity using photovoltaic effect. And this is basically what thermophotovoltaic conversion is. And here is a sketch of a possible device where you have a phase change material with a melting point beyond 1000 degrees that radiates photons, that some of them are converted into electron hole pairs in a photovoltaic cell that are collected and produce electricity, and some others, if not converted, they can reflect it back to the heat source, so increasing the efficiency. Well, indeed, thermophotovoltaic conversion is the only alternative for very high temperature conversion with a decent efficiency. In this figure, you can see the conversion efficiency as a function of temperature for several engines, including Brighton or Stirling engines. This is for the case of small generators used for space. But you can see that thermophotovoltaics indeed matches very well the temperature range of these phase change materials with a decent efficiency beyond 30%. Currently, the world record is about 30%. But still, 30%, if you are talking about batteries, could sound very small value if you compare with electrochemical batteries. So the question is this efficiency good enough for making electricity storage, for instance? Well, I don't have time to go into details, but this graph is very important and is indeed somehow linked to what Professor Laughlin just saw. But in this case, I'm showing the levelized cost of energy output of the storage system as a function of the cost of the energy input. No matter whatever you have in the input, either electricity or sunlight, it will have a cost. Even in sunlight, you have mirrors to concentrate the sunlight on something, so you have some cost involved with that. So the important thing illustrated here is that this kind of thermal battery, latent heat thermophotovoltaic battery, becomes profitable when you have very low cost of energy input. This is a very important characteristic, which is added to the long discharge time, as already mentioned by Professor Laughlin. So you have these two conditions, long discharge times and low cost of energy input. So this must condition the applications where you can put this system in operation. Well, just to illustrate a few embodiments for this kind of batteries. Well, I'm not going to enter into details, but the idea here is that you have to optimize the shape of the container because you must maximize the energy flow from the liquid phase to the thermophotovoltaic converter. So all these geometries try to do that. I will just show some details of our attempts to make this in practice. This is an illustration of one of the embodiments and the prototype that we have just built. So in some details, for instance, you can see here crucible, and here you can see the photovoltaic cell. This is a gallium antimonide cell, just underneath the crucible. And here, just one example of the system in operation with a hot crucible just radiating to the photovoltaic cell. Some examples of the IV curves that we got. One remark is the photovoltaic cell temperature, which is 36 degrees, which is quite low if in the one that is facing this very high temperature body. Well, this work has been done during the last 3 years in the frame of this project, the European Amadeus project. And one of the outcomes of this project was a workshop organized last year in November, where we invited other participants, as you can see here, people from MIT, 1414 and Antora that are also in this Colloquia. And an outcome of this workshop, if you are interested, it will be collected in a book that will be released in September 2020. So you will have more details on all this work there. That's all from my side.
Thank you, Alejandro. So we are collecting some questions. We're tabulating those and we'll get into them in a minute. I'd like to turn it over to Ashi right now for a discussion about what's happening at MIT.
Thanks, Greg. So this is just a quick cartoon overview of the embodiment that my group is pursuing. In short, we take in electricity from agnostically from essentially any source. We are on the regime where we're trying to push the temperature limit. So you can imagine an entire infrastructure shrouded in an inert gas. So everything stays in an argon atmosphere, and that allows you, that opens up the materials options for what you can use. So we are using an essentially all graphite infrastructure that allows us to go to extremely high temperatures. So we're essentially doing 2-tank thermal storage, but our low temperature is actually like 1900 degrees C, so our quote unquote low temperature. And the high temperature is like 2400 degrees C. So we take electricity off the grid, heat up the medium. In our case is actually liquid silicon, similar to Alejandro's case, but instead of using a phase change, we're actually using it as a sensible heat medium, stretching it over a delta T of about 500 degrees C, heat up the liquid silicon, store it in a hot tank, and then when power is desired, run that through a heat engine, which again, similar to Alejandro's case, is photovoltaic cells. So instead of trying to run turbo machinery, these temperatures, which would be exceedingly difficult, instead we go so hot that we can actually just convert the light off of the piping infrastructure itself. These cells, of course, are made in a very different way than normal PV cells. So these are cells that have a mirror on the back. So the majority of the light is not even, we don't even attempt to convert it. We only focus on the photons that we can convert very efficiently. That allows us to get the overall system efficiency higher. And all the light that is not converted then bounces off this mirror and goes back to the infrastructure, keeping it and retaining it inside the infrastructure so we don't lose that energy. One of the biggest, I think, contributors to us pursuing this approach has been a significant breakthrough that we've had on specifically on moving that fluid. So we've managed to figure out how to pump liquid metals at extremely high temperatures. This is a small excerpt from and a video from a paper that we published in Nature a couple of years ago, where we pumped liquid tin at about 1350 C. We have pumped silicon above 1900 degrees C now as well. Papers on that are forthcoming. But basically, we can now move liquids at extremely high temperatures, which now allows us to do new and interesting things. And this particular energy storage system is one of them that we're very interested in pursuing. Craig, you're on mute.
Thank you. I missed the click. Give Mahesh a chance to weigh in on the work that they're doing in Australia with 1414 degrees.
Can you see my screen, Greg?
Yes.
Perfect. Thanks very much for the introduction earlier, Craig. And I'd like to especially thank Professor Laughlin for the great presentation. I mean, he's explained the problem in very, very great detail and in a very exquisite way, all the problems with the negative pricing events on the grid, need for the storage as renewables penetration increases, etc., etc. And also why the thermal storage is a very, very attractive option. So my job has become much easier. So I'd like to take a slight segue from there, because right now we've only been focusing on using these thermal batteries as an intermediate for storing the electricity. But if you look at any country's energy landscape, here's an example for Australia. About 50% of the industrial energy usage is actually in the form of process heat. And interestingly enough, close to 40% of that process heat industry is for greater than 800 degrees C. So it's a very important space where most of the energy needs are catered for by the fossil fuels. And this is not just unique to Australia, but for every other country. And if we talk about a futuristic renewable economy where all of our grid systems are renewable, we have electrified most of the other energy industries. It's still very hard to electrify the processes which are above 800 degrees C. So there is a need for the green process heat at higher temperatures. And that's where I want to couple with the presentations from earlier, because we want to store heat at higher temperatures, but if we store it at high enough temperatures, we could use it as a mechanism for providing this green process heat as well. So what we're trying to do is quite simple. The 1414 TESS box that you see on the left side over here, that's our energy storage unit. We use phase change in metallic alloys, which are based on silicon. So these have melting point between roughly 1000 degrees to 1400 degrees C. And as Alejandro showed, the storage density of these materials based on silicon are quite attractive, and they are much higher than the electrochemical systems can get. We are agnostic to how we charge this thermal storage system. In the two demonstrator units that we have, we've shown we can charge it with ohmic resistance from grid electricity, or it can be done using biogas as well. So our second demonstrator unit is installed in a waste water treatment plant, which produces biogas, and that's used to heat our TESS system. And that heat is basically an energy cascading system, which can provide heat at ultra high temperature, medium temperature, or low temperatures, which can then be converted into electricity by running the gas turbine or a combined cycle, or can provide process heat. So some examples of process heat that applications that we're aiming for are the ultra high temperature processes, like the hydrogen production using thermochemical routes, iron and steel, the cement and alumina industries. And then in the medium temperature region is where we run our gas turbine or combined cycle. And at the low temperature end of the spectrum, there's a lot of process heat need in the pulp and paper, food, brewery industry, etc. So that's the sort of energy cascade that we are looking at. What we're trying to do differently from what has been done before is that mostly the energy recovery systems or the heat recovery systems for these power plants were aimed at the bottom end of the spectrum where the heat recovery was done. We want to do where it is more exergetically attractive. That's all I have. Thank you.
Thank you, Mahesh. So our final panelist today is Andrew Ponick, and we've heard about some of the high temperature storage opportunities. Andrew's going to talk about a little bit different range, I believe.
Absolutely. Thanks. I do have the benefit of going last, since everyone else has described many aspects of this system quite well. So I just have a single slide to go through what the team at Antora Energy is commercializing. And this has some similarities to what Alejandro and Ashe presented on. It's a thermal energy storage system using thermophotovoltaic cells as the engine to convert that heat back into electricity. The main difference is that we've heard descriptions of how to store the energy in sensible heat of a liquid, for example, in the molten silicon or in the phase change between a liquid and solid. Antora is commercializing an all solid system. So we use simply solid carbon, which has some of the benefits of very low materials cost and high energy density that Alejandro mentioned. But it does have the advantage that without a phase change, you have some simpler things on the system side. Again, it's direct ohmic heating of the carbon as the charging process, and a thermophotovoltaic cell as the discharge process. One of the things that Bob mentioned was sort of limiting entropy. I think the Malta or Bob's system it does a very good job of limiting entropy by using a heat pump. Another way to sort of limit the entropy generation in the system is to store the heat at such a high temperature that the conversion from from electricity directly into high temperature heat is actually not generating that much entropy. So this is what Amtor is commercializing. That's all I've got.
Thank you, Andrew. So at this point, we'd like to turn over the discussion to some of the questions that have been coming in on the from our participants. They're being tabulated by the team at MIT and kind of aggregated into a set that we can address. There's a couple of questions concerning the current molten salt system sizes. What are the largest facilities in the world? Where are they located? I'll go ahead and take that, given that I'm on the concentrating solar power side of the fence. I will direct folks to perhaps look at the Solar Paces website, which tabulates the number of plants that are existing around the world. In particular, the Solana plant in the United States was mentioned. That plant is a 250 megawatt capacity plant with 6 hours of storage. So we're talking about a plant that has about 1,500 megawatt hours of thermal energy storage, which I believe is the largest in the world. If not, it's very close to it in terms of thermal energy storage with molten salts. The most recent plant in the United States would be the Crescent Dunes Power Tower, which is also a molten salt facility. It is a 100 megawatt plant with 10 hours of storage. So that's about 1,000 megawatt hours of storage. And then there are a number of large facilities going in the Middle East, in Morocco, that rival those plants in their size. So there's more data on the Solar Paces website if you care to see more about that. So the next question I'd like to have for the audience is question about what are the other options for thermal energy storage. So we've heard about solar salt, which tops out around 500–600 degrees C. We've heard about silicon and phase change materials that are at very high temperatures. I'd like to hear from the panelists about other options that you believe may be viable and what temperature range that they're dealing with. So let me start with Ashi and let him weigh in on this. You're working with very high temperatures. Is that the range that you feel is the place to be?
Yeah, I mean, I think that I think staying at lower temperatures and using a heat pump is undeniably a significant contender. I think that the regime of going beyond 1,000 C has been largely underexplored, particularly if you're thinking about an infrastructure based on ceramics. I think that for many years, mechanical engineers have not really utilized ceramics as mechanical or structural members or members for piping infrastructure and the containment of fluids. I think that largely probably stems from the inability to weld ceramics, so to speak. So the notion of how you make joints and how you join things is not obvious, not straightforward. And so I think it's always been very straightforward to think about or restrict our thought space, our idea space to what can you do with metals, because we know we can weld them, we can make a gas tight or a liquid tight infrastructure that's reliable. But I think that there are some significant opportunities to think outside those confines, to think about other ways of making seals and making joints. And that's largely what my group has been focused on, is developing alternative ways of joining materials so that you can make liquid or gas tight seals at extreme temperatures that don't rely on metals, which rather intrinsically get softer and less stiff, less strong as they get hotter. Conversely, something like graphite actually gets a little bit stronger as it gets hotter, up to about 2,500 degrees C, depending upon the grade. So there are, that it's a very different class of materials that can have very different behavior. And I think there's some significant opportunities in that space as well.
Mahesh, you talked about the temperature range that your company is interested in spanning. Are you dealing with multiple storage media of that, or are you cascading the heat?
We do have different alloys at different temperatures that we're working with, but all of them are tailored towards high temperatures, so above 1000 degrees. But there are other alloys in sub 600 degree regions which show really good thermophysical properties required. I might add over here some of the work being done as part of the ASTRI and also in the US at NREL. So in terms of the options at lower temperatures, we do have chloride-based molten salts, which is slightly better than the nitrates in terms of thermal stability, but then there are corrosion issues with chlorides, and that becomes a sort of a research question. Other options are thermochemical based storage, and I saw in the participants that one of the researchers from ANU, Professor Wojciech Liński, was there in the participants. He could, he's been working on thermochemical storage for a long time, and so apart from those two, carbonate-based systems again come in the molten salt realm, sub 1000 degrees C. So most of these systems were tailored towards the supercritical CO2 cycle, slightly higher temperatures than what the nitrate-based molten salts can deliver.
Thank you. Any of the other panelists want to comment on alternative materials?
Bob,
Yeah. Oh, can I? I'm sorry.
Go ahead, Bob.
Greg? All right, thanks. So I remind everybody that equipartition is really strong principle. So for all practical purposes, sensible heat of all things is the same, which is 3 Boltzmann's constant per atom. It's the heat capacity. And therefore, the zeroth order answer to this question is it doesn't matter. Any substance will do for a heat storage medium. There are now, so the issue for me anyway of the medium rests on downstream questions of the engine that converts the heat back to electricity. So the vulnerabilities are kind of all there. That plus you don't want the heat storage medium to explode. So whatever it is, it can't have a high vapor pressure. So in that, by that metric, graphite is terrific. Now, so the engine is the problem, and always when you go to temperatures above the creep temperatures of steel, you have to worry about cooling. And that means there are entropy production issues associated with the cooling machinery. Semiconductors in particular have to be cold. They won't work if they're hot. The impurities in them will start diffusing improperly if they're hot. So they have to be kept cold. And so the cooling is a big constraint on how hot the storage medium can be and how close you can get to it. All right, so in summary then, I think the answer to the question, what other media are there? Any you want. You know, any medium will do as long as it has low vapor pressure. And then when you go talk about these very high temperatures, there are materials issues downstream for the conversion of the heat back to electricity that you have to worry about.
Let's talk a little about those materials issues. So one of the questions that came in concerns insulation. So from my own experience with molten salts, I know that the insulation can often cost more than the salt itself that you're storing. So at these higher temperatures, do you foresee or do you have problems with insulating materials in terms of performance or cost?
Yeah, that can definitely be the case, at least in our embodiment, where the cost of the insulation is more expensive than the medium itself. That's in a way a good thing and in a way a bad thing. So in a way, it's a good thing in the sense that the medium cost ends up becoming negligible by comparison to the container. But that's also to your benefit then to go very, very large. So when you go to very, very large storage, the surface portion of it, the skin portion that ends up containing the insulation, gets small by comparison to the amount of energy you've got stored and amount of material you've got stored, and so you can shrink that ratio of costs. And so that becomes an interesting place to play, particularly with Bob's pointing out that there's a need to look at longer duration storage beyond minutes and 1 hour or so, and to look into multiple hours and even potentially multiple days. I always thought the first company name was so clever, gigawatt day. Instead of kilowatt hours, it's gigawatt days worth of energy.
Can I have the floor a minute, Greg? He's absolutely right about this. All insulating materials are diffusive. And so if they're thick enough, you can insulate any temperature you like. And I honestly think for big deployments, you're going to use dirt. You just have an enormous tank and you put dirt. Dirt, of course, conducts heat pretty well, but if you have enough of it, it makes a nice barrier, and it's just literally dirt cheap. Right? Also,
Keep it dry.
Commercial insulating materials that have very low thermal conductivities, all of them use the same trick of having pores.
Yeah.
Those fail at high temperatures because of blackbody radiation across the pores. So all of these very high temperatures, you're all going to be retreating back to the basic thermal conductivity of solids. And the only way to get enough thermal resistance is to make it thick.
Agreed.
There is one point more to add here about the vacuum conditions, because if you want to make a good insulation based on thermal radiation, you want to make vacuum. So there is a trade-off there. We have found this problem of vapor pressure of what you are storing. So there is a trade-off. If you want to make a good insulation, you want to make a vacuum, but you don't want to evaporate what you are storing. So this kind of decoupling these two problems of thermal insulation and heat store, this is another thing that should be taken careful.
Yeah. Yeah, Andrew, you guys' system is operating at 1 atmosphere, right?
That's right. Yeah.
Yeah, I mean, we've thought about it the same way that, I think for many years there was a lot of TPV work looking at trying to pull vacuum to reduce the convective losses between the hot side and the cold side, right? But we just found it's a losing proposition. Once you get hot enough for TPV to make a lot of sense, you've gone so hot that pulling vacuum is just a nightmare. I mean, the vapor pressure of almost everything is going to be is too high.
And remember, the thermal conductivity of the vacuum goes as T to the fourth. So you just lose when you go with blackbody radiation up to high temperature.
Right. Unless that's what you're using to do the conversion.
It is. Oh, yeah.
So let's talk a little bit about thermal PV, because several of you are utilizing that approach for your energy conversion. What do you foresee as the major challenges in the development of TPV technology?
I'll comment real quick. I think Alejandro's got stuff to say too. I'll just say, to me, it's the reflector. Trying to, there's a lot of working knowledge and experience on designing PV cells for direct irradiation from the sun. I think there's a lot that can be leveraged in that respect, but it's almost a new problem to go back and rethink this problem from scratch and say the metrics of performance are different. And you say, well, I only want certain photons to get converted. I want everything else that I'm not converting to not be absorbed, because the intensities are much higher. The consequences on the performance of the whole system are much worse if you absorb light that you are not planning to actually convert, versus out in the sun, if you have some of the extra light that you're not really able to convert well, the penalty is much lower. So I think designing that mirror that goes on the back of the PV to reflect the light back onto the infrastructure, I think that's key. That's one of the big challenges, is doing that and doing it well. I don't know that there's like a real good metric on an intrinsic upper limit other than 100%. I mean, I think we can get various varying degrees closer to 100%. So I think there's a lot that can be done to try and get, every little decimal point, every additional 0.1% of reflectivity, or every fraction of a percent of reducing parasitic absorption really helps you there. It's a very steep curve on efficiency as you approach 100%. So I think that's a really interesting challenge. And I'm really excited and hopeful that folks in the optics community will get engaged on this problem.
Yeah, well, I can add something to that. Well, that's, I think, one of the three main things that matter for thermophotovoltaic conversion. That is efficiency. But there is another metric that is power density. That's in thermophotovoltaics, you know, that is completely different figure. And this is related with the cost per power. Well, and this is a key figure as well. So for reducing the cost per power, you must either increase the power or reduce the cost. Well, and I see that these are the two tendencies in research. Well, there is people that is trying to use low-cost materials for making PV cells. Usually this brings some losses in the power. And there is other people that is trying to increase the power per unit of area so that you can use expensive materials because they are producing much more power per unit of area, right? So I see that research is going in that way. I find particularly interesting, obviously this is a more long-term vision, but about the near field effects, the near field thermophotovoltaics. This is a really challenging thing, but I see that this is almost the only way to really enhance the power density. It's just basically consists on putting the emitter and the cells at nanometric distances. So then you have evanescent waves that can propagate into the cell. So you can enhance the power by a factor of 10 or even a factor of 100 to order of magnitudes at a given temperature. So you can operate at lower temperatures with a reasonable economics. I could speak very long about that, but I think these are the two main lines. I think the ideal, of course, would be to find an intermediate one. So, for instance, germanium photovoltaic cells, I think they are quite in fulfilling this trade-off of cost and power density. And in an implementation, for instance, putting the contacts in the rear to leave all the surface on the front very, very clear, to put in a near field arrangement. I see that this, let's say for a 10-year vision, would be a way for improving TPV.
There were several questions on TPV that we won't be able to get to, but I'll put them out there for you to consider. One question was, why not use a air Brayton cycle, combined cycle type technology, which would operate, commercially at 1200 degrees C instead of the TPV. The question was, how does that jive with Dr. Laughlin's statement that we shouldn't have semiconductors in our storage realm if we're talking about using TPV?
Well,
so building off of that one, I have the final question for you. So Dr. Laughlin really presented on a technology space that is lower temperature, say below 600 degrees C, using existing technologies more or less. And most of the panelists have talked about very high temperature, striving for high efficiency. So how do you weigh the balance between trying to come up with a low cost storage option, which may be of moderate efficiency, versus a higher efficiency technology, which may be of, technology that does not yet exist and is higher risk?
Who's this addressed to?
Well, this is addressed to the panel. So Bob, would you like to express your opinion? We just have a few minutes here to wrap up.
All right. This is a money question, and you can't address it without looking carefully at the market situation and the political situation. So the broad brush picture that we know from studies is that round-trip efficiency is not that important for the pure energy market because the cost of excess joules is so low. So right now, it's low capital cost that's important. However, the other side of the calculus is that this energy storage is an exceedingly political matter. And people not trained technically just don't understand if you tell them that you're going to store energy but throw away half of it. And for better or worse, that's part of the formula. So there's a sweet spot in the middle that depends on some bizarre combination of costs on the one hand and political stuff on the other.
I think I think I agree very much, and just would add, I think all of us are right now, it's interesting, we're at an interesting place in history in this problem where we're all placing our bets on which horse we think is going to win, you know, and it's an interesting time. I think everybody's got their bets placed, and I think more people, more folks in the science and engineering community are going to start placing bets and getting involved in this problem and figuring out where in this space they want to fall. I think the general sentiment, I don't know if I can speak on behalf of others, but we welcome you. I think we need more people working on this, more people thinking about this, and we've got a lot of territory to cover very quickly. But I think that there's a good shot that thermal may play a very significant role in solving the energy storage problem.
So that's a good segue to one of our poll questions I'll post now, which is, which temperature regime of the thermal energy storage options holds the most promise to solve the grid storage problem? So we're looking at kind of that promoted by Bob Laughlin, below 650, intermediate temperatures, maybe 650 to 1200. There's a lot of phase change materials in that realm. Or greater than 1200 degrees C, where we're talking about things that generally are solids or molten glass, very extreme temperatures.
Looks like everybody's scared of the heat.
Yeah,
you guys want to try to sway the audience?
You know, this is like playing Monopoly, and what you want is the oranges. You don't want those greens, and you don't want Boardwalk and Park Place.
Okay, so about half the audience is looking towards the lower temperature regime, where we can work with stainless steels, certainly with Inconel alloys, and some of the existing salts. So you guys on the panel, the rest of you on the panel, I got your work cut out for you to win over, win over our fans here. Okay, I want to kind of head into a wrap up here, and let me remind folks that we are still taking your questions. So will you use these questions? They'll help us with future colloquia as we try to set up for our future topics. You're also encouraged to sign up to the emailing list so that you'll be aware of the upcoming presentations. And our next presentation will be on May 20th, where we'll have Professor Jiang Yi talking about HVAC systems. So we are moving from the very high temperatures to things that are a little more accommodating for us here. Now I've lost track of the other screen. So I did want to post another poll before we wrap up. And this deals with the question of future topics. So this one's a little bit different. This is, you can select as many options as you like. And the question here is, which are the topics that you are most interested in for future discussions? And if you scroll down, you'll notice that there's two parts to this question, because we can only get 10 options per question. So feel free to click any of those topics you find interesting under number 1 or number 2.
And you can click as many as you like.
Yep.
This is definitely one of the coolest polls.
Yeah, this is one of the most useful polls for the organizers.
Absolutely, absolutely.
I would like to thank everyone that's participated today. At one point, I saw we had 530-ish attendees on in the webinar. So that's a wonderful turnout from all over the world. I think it's a tribute to the speakers that we have today and to the organization that MIT is putting into these efforts. Ashi, did you have any other parting comments you wanted to put forth at this point?
No, just if folks have other suggestions, these are some of the topics that we gathered from last week's webinar. If folks have other topics of interest or speakers to suggest, please put them in the Q&A. We do review them, and they may end up on another poll like this in the future. Let me share these results with everyone so people can see what some of the topics were that got some of the highest ratings of interest.
Yeah, it looks like the top scores here were in new materials and engineered thermal properties.
Mm-hmm.
And the waste heat recovery also scored very highly. And then there was a big cluster: battery thermal management, machine learning. It's a ripe ground here for future discussion.
Absolutely, yeah.
I did want to ask about the presentation materials. Is this video going to be available for people to view afterwards?
Yes, we're going to end up posting this on YouTube so people can view it there. They'll be able to review or see the slides that were presented via the video through there.
All right.
All right, with that, I think we can have the speakers maybe turn off their video. We'll leave the Q&A open for just a couple more minutes in case people have additional questions or comments they'd like to leave. And if any of the panelists have any parting thoughts they want to add, they can now. Otherwise, we can go ahead and probably end the session for today after give everybody a chance to write anything that they have.
Yeah, my parting comment is please, everybody send up prayers for us.